Hey guys, what's up? Time for another calculus video. This time, we're going to talk about the comparison tests. I think I'm back in my regular spot up here in the corner. Last time I was visually absent. Hope, did you miss me? I'm back. Okay. This is about direct and limit comparisons. So again, what do you need? A healthy respect for infinity. We need that every time. You need to be able to do limits at infinity, which I believe you can. And you need to be able to tell if something is bigger or smaller than something else, which might be a challenge. We'll see. All right, so let's get started. Let's talk about these three series. All right, so how would we think about these three series? Well, daggone, that first one over there looks like a daggone P series with a little addition on the bottom. That one in the middle sure looks like a geometric series. Oh, daggone, that one at the end, that looks like a P series, except it's got the little -1, right? They all remind me, and should remind you, of a series that is similar, except none of them are a P series or a geometric series. So what we're doing here is we're looking at these series like they look like another series, right? What are we doing? We're like connecting to we're like what's the word? Daggone. We're making them kind of feel the same. That's not a good word. What's a good word? We're similarizing. What's the? Oh, I got it. We're comparing. Okay, yeah, I should be an English teacher, shouldn't I? Oh, daggone. Well, we're going to compare series that look like easy P series or easy geometric series. We're going to compare them term by term. So we actually have two different types of comparison tests. One is called the direct comparison. One we'll look at a little bit later is called the limit comparison test. You can jump right to that one because I'm going to put the table of contents in the description below. Oh, by the way, why don't you hit that like button, hit the subscribe button, whatever the notification bell, do all that other jazz here so you don't miss out on any fresh calculus content. Yeah. So let's talk about the direct comparison test. The direct comparison test directly compares, what a good name for it. It directly compares term to term from one series we know about to another series we don't know about. And we can then prove convergence or divergence. So here it comes. It looks a little bit crazy. Oh my gosh, it's still going. Yikes. All right, so it says that if we get two sequences, A sub n and B sub n, and if you can establish that these two positive series, that B sub n is always bigger than A sub n for all n, then here's what you know. If the series A sub n converges, well, then you know I'm sorry. If the smaller series A sub n diverges, then you know that the bigger one also diverges. And if you know the bigger series converges, then you know the smaller series converges. Okay, I almost confused myself. But this kind of makes sense, right? If you can show that one thing is always smaller than a series you know converges, well, you know they both have to converge. If you can show that one series is always bigger than a series you know diverges, well, then they both end up diverging. So one thing you got to be careful about in this direct comparison test is the key is you got to make a judgment. You've got to make a judgment on which terms are bigger and which ones are smaller. And that you have to do that to do direct comparison. If you don't, you're not doing direct comparison. So sometimes it's easy to do to say that one series is bigger than another. Sometimes it's not. You'll see. I've got some examples in the coming minutes here that show you both. All right. So one thing you got to watch out for is that with this direct comparison test, it doesn't always work. It doesn't always work because if you know, listen, if you know that the smaller series converges, what do you know about the bigger series? Not really anything, right? Because what's bigger than a number? Well, other numbers, but also infinity. So what if you know the bigger series diverges? What's smaller than infinity? Numbers, like finite numbers, are smaller than infinity, but so are other infinities. Like you don't know, you don't know anything. So sometimes direct comparison is not going to work. And that's where limit comparison is going to come in. So stay tuned for that. Let's look at some direct comparison tests. So the first series that I showed you all at the start, 1 over n cubed plus n, that felt a lot like the p series 1 over n cubed. So I'm going to compare it to 1 over n cubed. What do we know about 1 over n cubed? Well, it's a p series. P is bigger than 1, so we know it converges. So here's what we have to do with direct comparison. Looking at term by term, 1 over n cubed plus n is smaller than 1 over n cubed, right? OE with the bigger denominator is the smaller fraction, right? So 1 over n cubed plus n is smaller than 1 over n cubed. So we just sealed it, didn't we? Because if term by term at the same n value, this unknown series is smaller than the known series 1 over n cubed, we therefore seal the deal in saying that the 1 over n cubed plus n series converges by directly comparing it to the p series we know about with assurance, 1 over n cubed, that converges. Okay, so there was another one up there. It was 1 over root n minus 1. You're going to do this a lot. You're going to use direct comparison a lot. If it's a p series, but close, like you're adding or subtracting something to the denominator, if you can see those, then direct comparison is pretty simple. But like I said, it doesn't always work. So limit comparison, stay tuned. 1 over root n minus 1. Well, that's a lot like 1 over root n, right? So you can't automatically say 1 over root n minus 1 is exactly the same thing as 1 over root n because it's not in that same format. Okay, so there's a danger in just like cutting to some conclusion that doesn't have any backing. It just feels like it should diverge, right? But you can't, there's no test that is based on your feelings. I'm sorry, there isn't. You got to use one of the legitimate tests. And you're learning direct comparison right now. So look at 1 over root n in comparison, right? In comparison to 1 over root n, 1 over root n minus 1, which has a smaller denominator, so it's the bigger of the two numbers. So 1 over root n minus 1 is bigger than 1 over root n. Well, that seals the deal, right? Because we know that the p series 1 over root n diverges. So anything that's bigger at every single term must also diverge. So the conclusion can be made that the series 1 over root n minus 1 diverges by direct comparison to 1 over root n. Direct comparison, really nice, really quick. As long as you can make that judgment, the greater than or less than, it's pretty easy to establish convergence or divergence. Let me show you one that's a little bit tougher. All right, so take a look at this, this example numero trace. Determine the convergence of, that looks nasty. What in the heck am I supposed to compare that to? Huh? What's that always bigger or smaller than? I mean, huh? I have no earthly idea what we're gonna do there. All right. So in cases like this, where it's not necessarily obvious what to compare to directly, or if the direct comparison test fails, meaning you get the bigger series to diverge, so you don't know anything about the smaller one, then the limit comparison can be applied. Okay, so the limit comparison test might be your go-to comparison test. You may just like completely forget about the direct comparison test because the limit comparison test will work where direct comparison fails. Check it out. So here's what we're doing in the limit comparison. What do you think we're going to do? Think we're going to use a limit? Yeah, we are. All right, so here's what the limit comparison test says. Check it out. So again, two positive sequences, A sub n and B sub n. This time, there's nothing about one being bigger or smaller than the other. We do not have to worry about one being bigger or smaller than the other. Here's what we will worry about. We're going to find the limit as n goes to infinity of one of those sequences divided by another. And it doesn't matter the order, just one of them divided by another. We're going to say that that limit is L. Okay, so you got to be able to find that limit. And as long as that limit value L is not 0 and it's not infinity, then the two series do exactly the same thing. They're either both going to converge or they're both going to diverge. Now, this is a little bit curious because, like, what the heck are we doing when we find this infinite limit between one sequence divided by another? Well, if you think about it, what we're trying to do here is we're trying to see that at an infinite level, do these two sequences, are they in proportion to one another, right? Is there a scale factor from one to the other? Now, if there is a scale factor from one to the other, then we know if a convergent series, if there's another series that's like double that one, well, we know that one also converges, right? But if we can get this limit, this infinite limit, this ratio between the two sequences, if we can say that one diverges and the other one is a third of the size of the, well, then they both diverge, right? So this is what this limit comparison test is doing. It's setting up a ratio. It's setting up a proportion between these two series. Okay, so maybe that should give you an idea of what this is trying to do. So here's what's happening. And again, it doesn't matter what the ratio is. All right, I say that right in here. It doesn't matter whether the ratio is 2 or a half. So you can like do 1 divided by the other, or maybe somebody else does it the opposite direction and gets 1/2 and you get 2, and you do it and you get 3, and somebody else does it and they get 1/3. It doesn't matter, right? As long as you get a positive finite value, then the limit comparison works, right? That's all we need. So just a rule of thumb down there. So if direct comparison works, limit comparison is also going to work. Direct comparison is maybe just a smidge easier. But even if direct comparison is inconclusive, then limit comparison is more than likely going to work. So what's that tell you? It tells you limit comparison is probably the better of the comparison tests, the more widely used. So let's look at example 3 one more time. It's that same ugly series that we don't know what the heck to do. Now look carefully at the power difference. Now, as n gets larger and larger and larger, the n squared and the 10n and the 27 and the n cubed and the 175 are not really going to amount to much. So as n gets really large, really the only thing that matters are the biggest powers. Now, we see this when we do limits at infinity, don't we? We just tie the limit to whatever the highest powers are. So we're going to do a similar approach here and recognize that this sequence is really like n cubed over n to the 4th, aka 1 over n. This series feels like 1 over n. Now that's important because what we compare to is important. And this one acts like 1 over n. Look, I'm looking at the power difference. That is big. The limit comparison works great for like polynomial divided by polynomial. Works wonderfully well because you can connect it back to a p-series. So here's what we're going to do. Yikes! We're going to take the limit as n goes to infinity of 1 over n. divided by the crazy series we don't know about. Now, if we pull a little bit of algebra, right, you can see that the limit as n goes to infinity is this n to the fourth over another n to the fourth, and that's going to go to 1. What does that mean? That means the two series, the yikes one and 1 over n, are basically the exact same series. They have a ratio of 1. That means they're basically the same. So what do you know now? Well, because you know that the harmonic series diverges, you now know that this crazy ugly series also diverges by limit comparison. What a wonderful test this is. Wonderful test. All right, well, I got another one for you here. All right, now this one, 3 over 4n times n plus 2. You might look at that series and go, oh, I know. Oh, I know what you're trying to do, Purvis. We're going to do partial fraction decomposition. We're going to get that thing to telescope, and we're going to find the actual sum. And oh, man, it's going to be so fun. Well, hold on, pump the brakes there, Charlie Brown, because you don't have to do all that. Look at that carefully. Look at the power difference. If all we have to do is show convergence or divergence, why go through all the pain and agony of partial fraction decomposition when we can just connect that back to 1 over n squared, right? The power difference, we got a constant on the top, we got n squared on the bottom, constants notwithstanding, it's the same thing as 1 over n squared. Let's see if we can create a ratio, a proportion between this unknown series that we're trying to show converges and this known p series 1 over n squared. Let's do it. So we're going to do the limit of 1 divided by the other. So 1 over n squared divided by the unknown series there. Well, you simplify that. You get 4n squared essentially in the numerator and 3n squared in the denominator. Well, folks, that goes to 4/3. Now, what does that mean? Oh, yeah. It just means that that's a real non-zero finite number. That means that the two series that I've compared are proportional to one another by a scale factor of 4/3. Well, what's that mean? It means they're going to do the same thing. Whatever one does, the other does. I know 1 over n squared is a convergent p series, so I now know by limit comparison that 3 over 4n times n plus 2 is going to converge. Now, do I know what it converges to? No, this test only tells me converge or diverge. It's just a test. It's not something that gives me any like real sum, right? That goes back to the question, the big question, does it converge or diverge? That's what these tests are for. And then what does it converge to? That's a much harder question to answer because we can only really do it with geometric and telescoping series. Now, if you want to do partial fractions and you want to write that out and you want to find the sum of that series, you most certainly can, because I did, and I got 9/16. Okay, I can do that. All right, so what have we done today? We've looked at 2 comparison tests. We've actually compared the comparison tests. Whoa, the direct comparison is nice because all you really have to do is say one series is bigger than another or one series is smaller than another. And then if they're in the right arrangement, you can say that if the bigger series converges, then so does the smaller. If you say that the smaller series diverges, then so does the bigger, but then it doesn't work out in the other arrangements. And that's where the limit comparison test is handy, because you're going to make an infinite ratio between one series and another. And as long as that proportion is a non-zero finite value, then the two series act exactly the same way as far as convergence or divergence goes. So those are the comparison tests. My money's on the limit comparison test, if you ask me. Next time, we're going to talk about alternating series. So stay tuned for that one. That one's going to be a lot of fun, a lot of plussing and minusing. You're going to see some pretty cool things about alternating series. So peace. I'll see you then. Later.